As we continue our discussion on concavity and inflection points, here's another problem. This has maybe a little bit of surprise in it, and we need to be prepared for these. Given the function f of x equal 3 over x plus 5, find the intervals of concavity and any inflection points. Now, the reason we might have a little surprise here is because this is a rational function. And remember, when we graph functions that look like this, lots of times we have different parts to it. We have vertical asymptotes and the different parts to the graph, because this is discontinuous at x equal -5. We have a break, and the graph is in two parts, and we call those branches. And anytime we have more than one part of a graph, then we can have different concavities on different parts of the graph, and so we need to be prepared for that. But as we go to find the concavity, we understand that the first thing we need to know is the second derivative. So that's our first question: what is the second derivative? And of course, the way we find the second derivative is we start out with the first derivative. So we calculate the first derivative here. Oh, I tell you what, before I do that, I look up here and I see that we really, it's of a type that we might need to use the quotient rule. But this one is simple enough that the quotient rule we can go around if we recognize that we can write this as 3 times x plus 5 to the power -1. That's the original function, and I'm just writing it a little bit differently. Then, in this case, then I can actually use the general power rule, can't I? Because what would happen for the first derivative, I'd take the -1 exponent, multiply with the 3, and get a -3, and then I would decrease the power on the parentheses, so I'd get a -2 power, and then I would multiply with the derivative of what's inside the parentheses, but that derivative is just 1. So I end up with -3 times x plus 5 to the power -2, which is nothing more than a -3 divided by x plus 5 to the power +2. Now, when I'm wanting to find the second derivative, it's convenient to find the second derivative by looking at this form right here, rather than looking at the fraction. And so when I look at that form, I take the exponent -2 and multiply with the -3, which will give me a +6. And then I would decrease the power on the parentheses by 1, and that would give me a -3 power. And then I'd multiply again with the derivative of the inside, which is just 1, so I'm not even going to write that. And so what I would end up with then is 6 divided by x plus 5 to the power +3. So there's my second derivative. That was a little easier than using the quotient rule in this case. Now, the next thing we need to know are the critical numbers for the second derivative. And so that would be two things. Where the second derivative is 0, we've been through this many times, haven't we? Where the second derivative is 0, or where the second derivative is undefined. And I think we've discussed before that the only way a fraction, see here, the second derivative being 0 would be 6 over x plus 5 to the power 3 is equal to 0. And the first thing I'd say is the only way we can have a fraction have the value 0 is if there's an x value that makes the numerator 0. And after all, the only way a fraction 6 or a 10 or 11 over a number is not going to be 0. The only way we can have a fraction be 0 is if the top is 0. And since there's no x in the top, there's nothing that will make 6 equal 0. No x will make 6 equal 0. So no matter what we put in for x in the bottom, we're going to have 6 over some number, aren't we? So this cannot be 0. There are no solutions to this. And if we ignored that and we went about trying to solve this equation, then what we would end up doing is we would multiply both sides of the equation by the denominator, because we'd like to get rid of the denominator. Okay, so we multiply on both sides by the denominator. And of course, course, on the left side, the purpose is for that denominator to cancel. We'd be left with 6. And on the right side, anything times 0 is just 0, and then we would get a silly statement like 6 is equal to 0. Well, whenever we see something like that, if we've done our work correctly, that's a big hint that our original equation doesn't have a solution. Because to have a solution, 6 would have to be equal to 0, and that's never going to happen. So there are no solutions to the equation 6 over x plus 5 to the power 3 equals 0, which means there are no places where the second derivative is equal to 0. So there are no critical numbers associated with that. But on the other hand, when we consider where is the second derivative undefined, because we have that x plus 5 in the denominator, if we used a negative 5 for x, we see that we would get a 0 in the denominator. So it's undefined when x is equal to negative 5. Okay, that's when it's undefined. And so that becomes the single critical number. Okay. So now down below, here's where we are now. We're going to begin to think about this. We've got a single critical number of negative 5. So that means that we have the interval from negative infinity up to negative 5, okay? And then it starts again at negative 5 and goes to infinity. So we have 2 intervals that we need to test. And what we're testing in those intervals is the sign of the second derivative. Because after all, what we're trying to do is decide where the second derivative is positive and where it is negative. And where the second derivative is positive, we know our function is concave up. And where a second derivative is negative, we know it's the graph of our function is concave down. Pardon me. So what we do is we look for a value of x. For instance, in here we might choose a value of x like a negative 10 or a negative 6 or a negative 7. Doesn't really matter what we choose. We choose some value of x in here. And so then we look at the second derivative. Now remember, the second derivative is 6 over x plus 5 to the third power. So we would substitute a negative 7 into the second derivative, and we would get 6 over negative 7 plus 5 to the power 3. Now, we can do these calculations. What we would get in the denominator, say, would be a negative 2 to the power 3. And of course, that would be 6 over negative 8, wouldn't it? The real issue, though, is that it's negative. Now, again, the point here is I could have told that I was going to have a positive numerator and a negative denominator at this second level. And that's really all I really care about. See, the issue is that the second derivative is negative. And when the second derivative is negative, that means the graph of the function is concave down. So that's really the information we were after. Now, we need to check in the second interval from negative 5 to infinity, and of course x equals 0 would be a nice check there, wouldn't it? And so we put that value 0 into the second derivative. Well, look what's going to happen. We're going to have a 6 on top, which is positive. And then when we put a 0 in the denominator for x, we'll have a 0 plus 5, which is positive, and when we cube it, it's positive. And so we're going to have a fraction that has a positive on top and a positive on bottom, and so we know the value of the fraction is going to be a positive. Regardless of the number, it's going to be a positive. So that tells us that the second derivative will have a positive value in this interval from negative 5 to infinity. And so that tells us that a graph of the function f will be concave up. Second derivative being positive tells us concave up. So now we know about the intervals of concavity. We're concave down from negative infinity to negative 5, and we're concave up from negative 5 to infinity. And it also tells us that we have a inflection point when x is -5 because we changed concavities. So we have a little bit more work to do to actually describe the inflection point, but we could say concave down on the interval, I'm just not writing out the words, on the interval from -infinity to -5. And we're concave up on the interval from -5 to infinity. Okay, now that inflection point business, okay, here's what we have to understand, is that we're getting a point value, okay, inflection point, and all we know is that inflection point has an x value. See, it has an x value of -5. That's the information we know, because that's where we have a change. And so we've got to know the y value of that point. Well, the way we find the y value, remember this is a point on the graph, not the derivative, or the first derivative or the second derivative. So we put that -5 into the original function. And look what would happen. See, I'd forgotten this. When we do that, you see, we get -5 over +5, which is undefined. Now, what I had forgotten, and this will happen to you, I'd forgotten that this function wasn't even defined at -5. I look up there. So if it's not even defined there, then there's no inflection point. Okay, we can have an inflection point where the graph is not defined. What we have is a vertical asymptote, so we changed pieces of the graph without an inflection point. So this is a strange situation where we can change concavities, but we have no inflection point. Okay, so we need to be aware of that. Go look at the graph here, and it will illustrate what we just discovered. We discovered within an analysis of it.
Okay, back we see the graph, just what we described, and because of that vertical asymptote where this function is undefined, to the left of that, we clearly see the graph is concave down, and to the right of -5, the graph is concave up. But of course, there is no inflection point. We just have a change in concavity because we have two different separate parts of the graph, two branches of the graph. We'll go on to another problem. That's the end of this problem, and we'll go on to another problem.